All right, in this example, we're going to look at actually writing the equation of a plane given some information. This example is pretty straightforward, but I just want to point out a couple of things about writing your answer in different ways that the answer might be given. All right, so we're supposed to find the equation of a plane containing a particular point, and the plane is perpendicular to this given vector. So the first thing we need to remember is what pieces of information do I need to know to write the equation of a plane, and can I write down that standard form for the equation of a plane? All right, so we talked about that in the last video where we talked about a plane, a vector perpendicular to the plane, the dot product of those vectors, that vector perpendicular to plane, with all the other vectors in the plane, that dot product should be 0. That's how I tend to think about this equation and remember it. If you have some other way to remember it, that's fine, as long as you can really remember it and not get mixed up where all the pieces of information go. All right, so the formula for equation of a plane, I've written an expanded form of the dot product here, is this. And the n1, n2, n3 are the components of any vector normal to the plane or perpendicular to the plane. Here we're given one of those. And the x naught, y naught, z naught are any point on the plane. We're given that. So for this one, really, once you remember the equation, it's just a matter of putting the numbers in. And then if you want to simplify, you simplify. One common mistake is students putting the wrong numbers in the wrong places. That often indicates to me that they have not really thought about what this equation means. If you think about this as a dot product of two vectors, you won't do that. All right, so the second component of my vector times y minus y naught. And then the third component of the vector times z minus z naught. All right, so if all I want to do is write the equation for a plane, I could stop right now. This is not in a simplified form, but it's the equation for this plane that they've asked me for. If I want to tidy that up and think about different ways that this equation might appear to me given to a plane, then you might do a little bit of algebra. You've got some distributing through parentheses you can do, some like terms to combine and some things like that. So I'm going to go ahead and skip a little of the algebra so we have some space here. But just to think about what we'd get if we write this in a slightly more simplified form. All right, so if I distribute through, I'll have 2x, and then I'm going to go ahead and move all my constant terms to the other side of the equation. That's a choice whether you want to do that or not, but that's often the way you'll see equations of planes given. So if I distribute this through, I'll have a minus 2 on the left side of the equation. If I add that to both sides, though, to get all my constant terms on the other side, I'll have equals 2, positive 2 over here. And then a plus 4y, and then this would be a minus 8 on this side of the equation, but if I add that to the other side, add that to both sides, I'll have a plus 8 over here. And then a minus 4z, this will be a plus 12, and then if I want to subtract that from both sides, I'll have a minus 12, and you can go ahead and combine these. So 2x plus 4y minus 4z equals negative 2. So that's also a correct answer in a more simple form. You might notice that for this particular equation, all of these coefficients and the constant term are divisible by 2, so it might be advantageous to divide through by 2 just to clean up that equation a little bit more. So if I divide through the whole equation by 2, I'll get x plus 2y minus 2z equals 1. So there's a simpler version of that equation. So all of these are correct answers, as well as any other equivalent way of writing the same equation. So when you do online homework, the homework system should accept any form of a correct answer unless it specifically specifies a specific form of the equation. These last two forms are in what is called standard form. And so that is in the form ax plus by plus cz equals d, where a, b, c, and d are constants. So that's standard form. Both of these are in that form. Oops, I noticed I messed up a sign here, didn't I? Caught that mistake, though. OK, negative 1 over there. All right, so standard form for the equation of a plane. So you can leave it in that form. Often when you're given the equation of a plane, not constructing the equation, but you're handed the equation of a plane and asked to do something with it, it will be handed to you in this form. So it's handy to recognize this as a form of an equation of a plane. There's one other interesting thing that I want to point out about when you're in this standard form and its relationship to this formula we use to write the equation of a plane. And that is those coefficients. Notice where these coefficients in front of the x, y, and z terms, I'm going to start with this form, where those coefficients kind of came from in my calculations. And you'll notice that in this first calculation, this first coefficient of the x came from my n1, and then the 4 came from my n2, and the minus 4 came from my n3. And so something that we will sometimes need to be able to do is to kind of work a little bit backwards to start with an equation of a plane and maybe be able to find a vector that is perpendicular to that plane or normal to that plane. And so it's not really anything to memorize, it's just something to notice in terms of the algebra of when you construct that equation and then kind of going backwards, that these coefficients, 2, 4, -4, are the components of a vector perpendicular to the plane. And even in this other form, the coefficients here, 1, 2, -2, would also be components of a vector perpendicular to that plane. Notice that this vector that I've written down here and the vector that we started with are scalar multiples of each other. So those two vectors have the same direction, different magnitude, but those two vectors have the same direction. So those two vectors are scalar multiples of each other, both perpendicular to that plane. So that's a handy thing to be able to do sometimes, is to be able to take this standard form for an equation of a plane and kind of work backwards, find a vector perpendicular to the plane, or find points on the plane. We'll look at some other examples, writing equations of planes and kind of working forwards and backwards with those equations to analyze different things about the geometry.